Yeah, thank you for being here. You can tell that I'm from the German office of Autodesk coming here, and it's right that my favorite part of Maya currently is Bifrost. And I was preparing a talk about these topics here. Actually, I had animation in there, but I realized that I have to, strike it down a little bit to show you not everything that you can do in Bifrost, which I'm really tempted to do, but concentrate on a few things. And modeling will be the biggest chunk of the whole thing because I'm currently on a modeling project that is very interesting that, of course, I would like to show, but we also talk about what's possible in rigging and visual effects in Bifrost. Again, visual effects, just a small snippet, Bifrost is very much about visual effects. So we can't do that in 45 minutes, and I have to hurry up because my colleague is right after me after this presentation. So let's jump right into it. The agenda, as I said, is modeling, rigging, and visual effects. So we're going to talk about a few projects here. In the upper left, you see the modeling stuff that I brought here, some of the rigging examples that I have here, and a short overview over what you can do in visual effects. So let's talk about modeling. So what can you do in Bifrost in modeling, or what do we call modeling? You can load in models from Maya, and then access these models and modify them. This is a good example. That head was modeled maybe in Maya, or maybe converted into Maya, and then in Bifrost I can deform it, I can do extrusions, I can split faces, delete faces, yada, 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 the whole range of possibilities I can do there. And of course I can also analyze and fix things. So if there are holes in there, for example, or double vertices or so, I can find that out and fix that stuff. Another thing that we can do modeling-wise, I count that to modeling because you're creating models of landscapes when you do scattering, instancing, like, set dressing. You won't have rocks and pebbles and grass and plants and trees and everything in the scene that is instancing. So you are placing models and you create a final model from that. And then the stuff that I'm currently working on is procedural modeling. How do we make a construction history in Bifrost to create models that you normally, it would be tedious to do them by hand. So for example, buildings here you would do rather in an architectural software to get forward. So we will have a look at that. The current status is that we have quite a few nodes already that access polygons, that access the structure of a polygon object. So you have, of course, the points in an object, but then you have description of which points are used for a face or for a facet. Then you have information about UVs, so different UV sets in there and stuff like that. And you can have additional information. So all of these nodes handle all of these informations and allow you to access and modify polygon objects here. So when we talk about procedural modeling, like this one here, so we're going to come back to that example here, we tend to forget the advantages and the disadvantages of procedural modeling. Some are really advantages, like you have a construction history and you can change everything just so. But to define that construction history is a little bit tedious because of when we look at procedural modeling, we tend to think like, okay, this is a construction history. I have a base model, something where I start. Maybe I create it from scratch, or maybe I have it already. And then I have steps that I do to create my final model. But what's missing here are parameters. So for all these steps here, I need to input some parameters. And sometimes these parameters are fixed. Like I have an extrusion depth, and sometimes I want them to be variable. I want to do, different extrusion depths in different places. And another thing that gets forgotten is the selection. So when I model interactively and make a construction history, I can point at things and say, this facet here and that edge I want to modify. When I do procedural, it has to work by itself, so it's not working. I can show you what I mean with that in a second. So in this example here, when we talk about these operations that we do. A sequence cut, for example, would include the different sizes of the street level here, that little rim and this strip here, and the little rim, and then the windows that we have here, and the rim and the strip and the rim again. So that is a sequence of cuts that we do in this building. So we have a node called sequence cut to do that kind of stuff. We have an extrude node, we have instancing nodes to place things, etc., etc. So all of these nodes I call the hero nodes in my system, which when you read the names here is called PPG. I call it procedural polygon generation. So I procedurally model something. You would then chain these operations together. So you see it's a long chain of operations that results in a final output back into the Maya scene. So it spits out a Maya or a polygon object that is colored, has materials, for example, and is actually ready for rendering and can also be converted to a Maya object altogether, because while it's alive, it's a Bifrost object. So here's the thing with the selection. Normally, when I select something, I point at the facets, for example, click them, then they are selected, and then I make an operation like an extrude, and that's it. The problem starts when you change the underlying start object, like I change the resolution of my cube. So I add more polygons to it, so these numbers that I clicked on are somewhere else here now in this final example. So procedurally, what I would do is to say, hey, instead of clicking on these polygons, I'm placing a selection object over them, like a cube volume, for example, to say, okay, these in the volume, these are extruded, and now when you move the volume around or change the resolution, then of course you have something that works procedurally. Even with different starting objects or different starting conditions, you would have the same result. So there is a number of selection nodes that would select something by their normal, what direction is that object, is that facet facing, or randomly, or by shape, for example, or by their area, or something like inside the mesh, what we've seen with that cube, moving around and say, is it inside the mesh? Yes, then select it. So you have another set of nodes that do exactly that. So you have a collection of commands that you can use in your so-called construction history. So when we go back to this example here, we start with a geometry, with an underlying geometry, and then we select faces, and then we do something with them. So we cut them in one direction, we cut them in another direction, and set up this model operations. One important part here that people tend to forget is the diagnostics while you do that. So once you start to cut things up and you only have a gray object, you lose your path immediately, because after the first few cuts, you don't know how do I select the other objects. Because there's another selection mechanism that I call the phase tags. So they get names. We collect them under names. And these phase tags are what create these colors here. So I have Maya here in the background and one object already loaded. So it won't let me get there. So here we go. So this balcony object here is created entirely procedural from one single polygon. And I can show you that because here in this construction history, I set it up so that I can select this node here, and with this number here, I can control the number of steps that we do. That's the one single polygon where we start. And that is the first step here. So we do a cut, a horizontal cut to make this plate for the balcony. And then we extrude the balcony, and then we cut the balcony itself to have some sort of a rim around the balcony, and go on with the cutting, and then we place some poles here, and so on. So you see how this whole thing is done. So after a while, we start cutting the actual back of the balcony to make a door and a window. We split the window part into half. We extrude it, and we extrude it, and we are done. Right? So that's all completely procedural, works on different kinds of polygons with different sizes also. You see that, I hope you can see that in the projection, that all of these faces have nice labels That is something very important to see what do I need to select next. Is it the window frame, to do something with it? That kind of stuff. If you don't have that, it's really tedious to take track or to keep track of all of these things. So another example of that would be the building that we've seen all the time. So I have a similar setup here for the building. So I pick this one node here, and the first thing that I do is to extrude this, what I call the penthouse, and then I put a roof on it with one extrude and another extrude, so extruding and offsetting to get some sort of a roof, and then a subdivision for the penthouse. So I have a node that subdivides, and you can tell if that thing is bigger, just keep subdividing. I just say how big I want to have the subdivisions, and then it, calculates how many subdivisions would fit into this space here and keep subdividing. So when I pick that cube that is underlying here, the starting object, and scale the whole thing, you see that it keeps subdividing itself depending on the size of the whole thing. So the next step would be to cut the whole thing into several strips. So this is a sequence cut, and the sequence with these rims and strips and so is flexible only in one place in the middle here. So the pink part is flexible. Next, when I cut the pink part here, then I can say, okay, scale it and just make more floors here in the pink part, depending on how big the underlying geometry is. And then I cut the whole thing vertically, and you see where it's going. I cut it vertically, and then I go extrude it, cut and cut and cut, extrude it. And then we have a special point here where we do instances. So these arches here are instances, and also what appears here at the bottom at the street level, this is an instance. That was too complicated for me to model with a procedural, so I modeled it by hand and just put it in place, and it gets stretched so that it fits the underlying polygon. Right? So once you have done that, you can go in and say, hey, what about a different starting topology? It didn't work here. So what about a different starting topology? Maybe an L-shaped polygon that doesn't have bevels at the corners. So now I can subdivide this underlying object if I select it. I don't have. So if I select this underlying object and scale it, you see that the whole thing subdivides itself. And you see, of course, the construction history struggles with rebuilding that building few times per second, but it's pretty fast already. Right? So let's go on and see what else we can do here. Okay. So here's another example. The colorful building is, of course, very nice as a toy-like example. But I wanted to have something that really looks like something that you could use for an architectural rendering, for example. And let me switch back to Maya. So this example is this one over here. Takes a moment to load and to create, actually, before you can see anything. And you see the construction history is quite long. But this thing is really amazing, and I don't need to see that construction history, and also I don't need a shelf here. So the thing is really amazing because it also started from a single polygon or a cube. So the only thing that I had here in the outliner, I can pick that cube, was that underlying cube. And when I scale it, you can see, oh yeah, it's really slow. But it keeps subdividing all of these apartments and all of these, variable floor layouts that I have. So with sequence cut, I made different sequences for the floors to have larger balconies and smaller balconies in an apartment without a balcony and so on, and randomly even placed some lights in that object here. So I can now make a vertical building out of that by just scaling the underlying cube. And you see, okay, it struggles with the speed a little bit, but it's still pretty fast to create that thing. So let's go in and maybe start a GPU render of that thing and see how that holds up. And actually, my laptop is not loading, and that's why it's pretty slow here. Now it should be loading. And you see, it's not bad. I mean, for something that you can change in a matter of seconds, it's not so bad. You want a different layout, more apartments, more floors. Yeah, I can do that in the matter of seconds. Good. So let's go to another example, because I didn't stop there. Once you have a building, you want to start to make a whole city. How about that? And here you see in this animation already how it goes, because I start with something that is actually not a city, I'm just extruding blocks. And these blocks here are my starting points for the different buildings. Trouble is, when you want to make a city, you would be amazed how little you can do with just 3 buildings or so. So I made 6 buildings at least, which still looks boring because you look at it and you see all the duplicates. So I started to figure out and try to make different variations on the shaders, like a more greenish glass, a more bluish glass, more bluish facade, or reddish and stuff like that. You see it in the second image here when we look at these candy color buildings here. So many of these buildings are of the same type, but they have different colors, and that is the material variation that you can see. So let's go back into Maya and load that scene. I would load this one here. So I'm not going to convert the city to the final stage. So this is the whole city that you just seen here in the blocks. So let's go closer to these blocks here. I hope you can see that. And they have funny names. So this B1 and the numbers and an F, that is the facade. So F at the end means facade and R at the end means roof. These numbers here stand for a material variation. So one number is interpreted for the facade, one is the glass type, one is the roof type, one is another facade material if I need more than one, and so on and so on. So that way I can randomize all of these buildings even further. Even if I don't only have 6 building types, I have like hundreds of material variations that I could do. Just go a little bit further with these materials. So how do I turn this into a big city? So this city now has 780 buildings, which is not bad for just procedural. If I turn that into the full-blown geometry that I was rendering, it would take like 15 minutes to create all the geometry, 4 million polygons, and would save it out as USD immediately. Just, that's the easiest part, save out as USD. There are materials already assigned, and I can assign more materials by adding another USD layer with the same material names that I have already, and suddenly I have a rendered city. So once that is established, it goes very quick. So let me show you here. I can scale down this base layer here. Let's make a very small one so that we don't wait too long for it. And when I open the Bifrost editor and turn on, just wait a second here, and turn on one switch that I have in there that is there to make this decision here. Do I need to create the final thing? So I'm going to create the final thing here with this switch, and should take like 10 seconds or so to make these kind of 20 buildings or so into the final resolution. And you see all the detail that we have here by just turning on this switch. So the next stage would be then, now it's written already out as a USD, so I wrote out the big city USD and load that back into the layer editor. So that is the final city with the diagnostic shaders. So and how do I put on the other shaders here? So in the outliner, when I have my USD layer editor on, actually USD layer editor is okay. So here are my layers. That is what we see here, the big city with all the 4 million polygons. And this one here is just materials. So I made one layer with just the material names that I have already, class 1A and B and C and D, etc. And these materials get sorted into the final thing. so that once it's loaded, I can immediately click on rendering. We see the previous image, and here's my city. And it's done rendering. It's amazing, isn't it? Like 4 million polygons and I don't know, 25 different materials. It renders like easy peasy. So I'm really excited about this thing. I keep working on it and try to keep the performance up and improve the performance so that you can, sooner or later when I publish that, you can use it yourself and make that thing. Let's go back to the presentation because I have more things to say about this. So here is a short movie of what I do to create this whole city from one polygon. So we've seen the one polygon. I cut something in an angle. That's the Broadway. You know, in New York, for example, you have the Broadway going right through the city and different from the city grid. Then I cut the city grid, and now these yellow ones here are blocks of buildings. So on every block you have a number of buildings. So I need to subdivide these blocks even further, cutting this way and cutting that way. And then JP asked yesterday when I showed him that, but then your buildings don't have any distance between them. Yeah, make an extrude. Oh, damn it, sorry. Make an extrude. Just let's play it until we are there. Make an extrude with an offset so that, you know, you get your... I clicked it again. I did it again, sorry. Here you go. So make an extrude to make the space between the buildings. And then what I did, the center piece of this extrude had all the same name, the same type. So I have a node that simply, where you say, I have these in this case, 780 building blocks. Now divide them up into 6 different types, 6 different building types. And for each of these 6 different building types, I also assign, these 5 or 6 numbers for different material variations. And then I get this. So this is my groundwork for the whole city. And this is really quick. This is really interactive. You can size it and you play around with settings and so. And when that is done, I turn it into USD and then I get this one here. That's the final model. And as I said, it's not very interactive, so if I want to make changes, I have to wait like 15 minutes or so. So I write it out immediately as USD and just to say, I have this. So I can go back and change my underlying, my groundwork here for the city, and I can go from there. So this is actually what I wanted to play as the final for modeling in Bifrost. That's what you can currently do, and JP said very well, needs some lighting. Yeah, sorry, I didn't have time for that one here. So, but it's nice, and I enjoy doing that here and to randomize everything and to mix it up. The only thing that I can't do right now is very old buildings, like when we see here in the city and have all these old material that is there, old roofs and different types of, Baroque buildings, and so I can't do that currently, so I'm still working on that. Yeah, ornaments, and so that would be instancing then, have an ornament and build that from there. Okay, so let's jump right into rigging here. Why would you want to rig in Bifrost? Because you want to go from this one here. I don't know if are there any riggers here? Any riggers among you? If you see a rigger work, he works with shit like this. That's why these people are crazy. And of course, they want to go to do something like this here, to have an element that, brings calm into this whole chaos, and at least, takes all of your bones and positions and translate that into in a proper movement without going crazy with all of these nodes. So we have 2 examples here. This one here is a shoulder module that we have already, that works already. I'm really surprised. So this shoulder module does already what it shows here. And this one is really cool. And actually, I have this robot, so I'm playing around with this robot. So we have the situation that we have here is 1 axis here, 1 axis here, 1, 1, 1. So we have all these ones. And the math behind it, behind the solution, so that it always comes to the proper end position when you grab the IK handle, is a mathematical wonder, I would say. So this guy really knows what he's doing. So it is actually, it's the math that you can do and have a really smart and fast IK handle by yourself. So regular IK handles cannot do this, cannot solve this thing with all of these one-axis setups here. So that is very cool. I really enjoy that. Another super cool thing when we talk about rigging is this one here. We do machine learning. Okay, yeah, again, AI, yeah. It's kind of boring in one way because nobody understands how the hell that's working. Machine learning, as in contrast to AI, machine learning is just what we call a neural network. So you know these graphs where all of these little neurons are meshed together and somehow you feed in something and it spits out the correct solution. And that's what Bifrost, actually not really Bifrost can do. What you can do is to say, hey, I have a situation and I have, a number of solutions here. So for example, for the IK thing, for rotations of my bounds, I can tell you where the endpoint sits. And I want you to deliver me a network where I can take my IK handle and you do that automatically without infinite number of points. You just estimate where I want this thing to be. And the setup is so that you then write out the data and train a network or train the neural setup and load that back into Bifrost and set up a network in Bifrost, and that really, and that is the surprising part of it, that really works. I can't actually believe it. So here is that setup with the points, with the data points. We have this weird arm thing here where we also have, single axis and a weird setup with too many joints and too many single axes so that a regular solver can't do that actually. And then in Bifrost, we have this setup, and it's all well documented, where we can go, and I think it was in here, double click in here, yeah. In here, we have the possibility to say, okay, you want to try out these angles here, and the point cloud results in this point cloud. I can also say I have more data points, for example, if it becomes too thin. So this is the range where this robot arm will later be able to move. As I said, you write out the data, you train your neural network, and then you load in that neural network into Bifrost. And I can't even show you what that looks like because it's all packed up properly, but you can open it up and have a look. So there are stages for this neural network to react to that IK handle movement. So when I pick up this IK handle, it moves properly within these data points, only in the area where the data points are. It moves properly, but there's no IK handle here. It's just the neural network that spits out these rotations for the arm that are necessary. And when I do something wrong, you see, oh yeah, now it freaks out because I'm outside the data points. So there's no solution for this thing there. But this is an easy way without math, actually, to set up stuff that mathematically would be quite challenging and probably sometimes not even possible, because sometimes when you look at the blue robot that I showed you, you notice that the base of the robot is always flipping backwards when you get close to that robot. And you pull it, and then it rotates in one direction, and you pull it out. But this solution is so that the base has always to rotate. If you want to have a different thing for the base to do, like don't go so far, so don't be the first to move all in, but move a little bit maybe to reach that point, that would be something for this here. So you could do the blue robot as well with different results, so to say. So I would say we leave it there with rigging with these two examples here. What you can do, you can build your own solutions, IK solutions, your own setups, but you can also train, a neural network to do that. So let's jump over to visual effects, because JP is already getting nervous, like, can I? No. Okay, so Bifrost, when we as Autodesk talk about Bifrost, we always, think about explosions and fire and smoke, etc., because that was the first thing that was there, and it was very, it's pardon me, it is the first thing that comes to mind, let's say it so. So we always have these wonderful powder explosions here with colors and we forget about the smaller things that you can do, like a rig setup, for example. So what you can do, or the good thing about these simulations is that you can touch them and change them. If you know how these simulations work, of course, if you have an idea how smoke and fire get simulated, you can go in and open it up and make changes. So we have ready-made examples and setups for smoke and fire, for example, for explosions, for these fiber solvers, for the thing that we call MPM solver, so anything that acts like snow and sand and anything in between can be simulated with that. We can simulate cloth very well. There is a particle setup built in. I mean, particles are nowadays, it's just easy peasy. We can do that quickly. So that's already built in. Then, recently we had an update to get better cloth solver functionality, this simulation of the BOSS, the Bifrost Ocean system, where you just simulate a surface with a special algorithm and some textures. That's really cool because it looks super natural and it's extremely fast. It does not solve, or it does not create a deep ocean, it's just a surface thing. And of course, smoke and stuff like that, we can do that. And you see here down at the very end, liquids are very new. So a thing that, and this is actually an in-between here. So this gel is an in-between, something between sand and snow and a liquid. So it's a sticky, gooey thing where you can have ice cream or honey or chocolate and all that stuff, simulate that. We have a new NPM rubber in there, and we have this nano VTT viewport rendering, which is amazing. It shows amazing quality when you do a viewport rendering. Let me load one example here, which is actually, unfortunately, a little bit slow, this one here. Oh, I need the timeline, sorry. At least the timeline. Yeah, but to show the viewport quality, it's actually, that's okay. This is cached, so that's why this thing can load the final result already. That's really bad to see here. Let me darken the background a little bit. That's very hard to see. So that is a ready-made explosion that you can drag and drop into Maya. So here in Windows, you find the Bifrost browser, and this Bifrost browser allows you to play around with, ready-made scenes that are there to show you examples. All of these scenes are documented, so you can open them up and see how it's made. And for example, with this rocket here, you can see how do I hook up my own rocket in this, my own, thing that explodes at the end. That's this one here. So you simply double-click and it imports it in normal. So the regular thing would be to import it, but here you have all of these examples that you can play around with. So in the Bifrost browser, I simply drag and drop this into my scene, and then clicked on the cache node. There's a cache node in here to store all of these settings for the different files. And the result, for something that I just used there from the browser is not so bad. So coming back to that water thing here, that is a brand new thing, liquids in the graph. We did have liquid simulation in Maya before, and it was even Bifrost. It was called Bifrost 1.0. and it was an interactive way to create water simulations, or liquid simulations, as we call them. It was interactive in a way that where you could say, okay, I have this object that emits the water has this and is an object and has these and that properties. Here's a collider for the water and stuff like that. So you could set them up interactively, which is cool, because it's much easier than to mess around with a graph, right? But the problem is you cannot change the way it solves the whole thing. So if you have your own solution and you know how to go faster or have better results or different results for different kind of water, then of course you couldn't do anything. So now this is a 5-minute setup of water. So literally create 2 cubes. One is the emitter, the other one is reversed, and the opening is deleted. That's why it spills a little bit of the liquid on the side, and I added a kill plane to catch the spill. So that is an easy setup for water right away. So that is super, super fast. This one here was created by the developers as a test, how stable is the whole thing. And you can see, whoa, yeah, that's quite some volume. And that is not done in 5 minutes. That takes quite a while to simulate, because when you have the basic settings, you would crank up the resolution and do everything to make it faster. Just a short jump into Maya. I want to show you how you start to set this up. Come on. So you delete everything. You create a graph. And I need some more space. So let's say you want to create a basic a liquid simulation. So what you do is to hit the tab key and start to type basic. And here are our basic graphs, basic graph setups. When you click on them, so for example, here's the liquid graph. When you click on them, it's a bit disappointing, the graph that you get there. But the point or the thing is that what you want to do with it is you right mouse button on it and click on explode. And then you don't get 100 nodes, you get 4. So usually it's 4 or 5 nodes that you get, and they are the source, the colliders, and the settings. And there is room for you to add other settings. So here influences, for example. So if you want to add a kill plane to catch all of these, it's not even in here, damn it. So if you want to kill plane, you have to type kill, I'm sorry. Here's the kill influence. So it's a kill influence that you can also plug into this thing. So you are able to enhance this. And if you want to change the whole solution, so here I would hook up the cube that emits the water, and here I would hook up the cube that, or any colliders that I have here. And then I double click on this one, here would make my changes. This is the simulation, the heart of the simulation. This is it. And it says, simulate liquid internal. Okay, I can't change it. It says it's not editable, but I can make it editable on the right mouse button, make editable, and now it's mine. Now I can change everything and take it apart and change the color of the points, change the way it's simulated, everything. All the forces that are in there, I can change that. I could write my own solver. And by the way, I wrote some solvers, not for liquid, but very basic stuff like inertia, a jiggle deformer. You can write that yourself in Bifrost, and it works quite amazing. Easy peasy, so to say. So, beautiful water simulation. So what have we got here? Quick wrap up, and we are a little bit early even. I could have spent so much more time. Oh, Jesus. So we were looking at modeling the different kinds of, setup for a construction history here. We looked at rigging this beautiful blue robot solver or neural network machine learning solver. And it's funny when you are so close to machine learning that you actually could do it on your own computer. You only need to install a Python library and suddenly you can do machine learning on your own computer. That's amazing. It's a bit scary. I have yet to try it with the blue robot. I'm going to do it. And then we looked at visual effects, what's possible there, and even had a look at this liquid solver here, the basic liquid solver in the graph that you can change yourself. You have NPM snow and sand and particles and cloth. All of these solvers are available for you to open them up and to play around with the whole calculation. So, that is the presentation so far. As I said, I would have loved to spend more time with this modeling stuff because that's real fun. To not only to build it, but also to optimize it, you know, to crawl in and optimize and see, okay, I'm wasting time here by the way it loops over the polygons that are in there and stuff like that. So that's really interesting. Okay, so one of the main advantages of Bifrost so far is that it's integrated in Maya, because you can not only save USD out in an instant, you can also look at the USD that you create in Bifrost. So if you make a whole USD scene in Bifrost, you can already look in Maya. Maya is the viewer here for the Bifrost scene, so there's no need to write it out and load it back in to see if it's correct what you're doing there. That was my presentation. Now is the time for questions, if you have any. No? No questions? I'm going to be around. I'm going to watch JP's talk. So if you think about questions, you can come later to me. Thank you very much. Oh, there's a question. As far as I understood it, that is the plan. That is the plan, to have a Bifrost executable for other softwares. I have heard there is something around, but I don't know if we already offer it for purchase.
Any estimations?
Pardon?
Any estimations for?
I can't, because that would be announcement already, so I can't say anything. Even if I had an idea, so I don't know when. Yeah, as far as I understood, that is the plan. Yeah.
They would kill us.
They would kill us.
Yeah.
Okay, thank you very much. I'll be around if you have more questions. Thank you.